So we'll continue with talks this afternoon. Please welcome Matthew Rocklin, who will talk about Dask and Jupyter.
Hi, everyone. My name is Matt. I work on Dask. So Dask and Jupyter are kind of weird in that, in some sense, they have nothing to do with each other. One is about scaling out computation, parallel computation. That's Dask. One is about interactive computation. That's Jupyter. They're actually both technically very similar, though, in that they both serve the data part of Python and using the networking async concurrency side of Python. When we first started Dask, if you want to have many different Python processes talk to each other, they actually both do that. When we first started Dask, we actually reached out to the Jupyter maintainers, and they actually helped us a lot early on. And as a result, the two projects are actually pretty close in terms of underlying infrastructure and in terms of community. There's good folks that I think there's a lot of strong relationships. And there's also a lot of very good collaboration on the projects technically. This talk, I'm going to focus on two different sort of smaller talks. We'll talk about different parts of that collaboration. We'll talk about interactivity and diagnostics and sort of how Jupyter allows Dask users to see a lot about what's happening with their computations, which has a lot of value. We'll get into why. And then a totally separate topic, we'll talk about sort of cloud notebooks and scalability and adventures or misadventures in doing that, and sort of where I see that space. So first, interactivity and diagnostics. They say you should start off every talk with a statement that is obviously true. And this is my statement. Computing sucks, and it especially sucks for distributed computing. Distributed computing really sucks. When something breaks in your computer, if you run out of memory, if you are using all of your CPU, you have tools. You will bring up top. You'll see that your fan starts blowing. If your computers are 100 computers on a different continent, it is harder to run top on them and see why things are broken. It's harder to look at logs. And so interactivity is really important, and diagnostics is really helpful to address that. And Jupyter really helps Dask users play with that interactivity when things break. So I'm going to go through a demo, and we're just going to kind of see how Dask gets used. And then we'll sort of highlight a bunch of different things that came out of that. So I'm going to switch over to this notebook. I like starting off talks with demos because they're fun. I was talking to Thomas Caswell, who helps to maintain matplotlib, and someone told him that about 15% of journal articles, so scientific journal articles hosted on archive, use matplotlib. That's a big number. It helps him get funding, for example. A lot of science uses his plotting library. And I said, how did you figure that out? He said, oh, I think someone somewhere scraped through all the PDFs on archive. They host all the PDFs. And they came up with that number. I said, great, let's go and just do that analysis. So let's go and do that right now. So there's an S3 bucket archive, which hosts every PDF ever published on archive. And there are about 6,000 of these directories, which are stored as tar files. And if you're a scientist, you're not surprised that they're storing a bunch of PDFs as tar files, a very Baroque storage mechanism. And this data is, it's about 3 terabytes. And so we are, in the next few minutes, going to process through 3 terabytes of PDF data on archive. That's kind of what Dask is good at. Dask is good at doing janky Python code at scale and allow you to process lots of data very easily. So I've written this janky Python function. It opens a directory. It opens a tar file in that directory. It iterates through all of those different files. It finds all the PDFs. It then checks to see whether the bytes matplotlib are inside of that PDF. It turns out that matplotlib started watermarking all of their PNGs and PDFs with the bytes matplotlib, so we can easily tell if a file contains a matplotlib image. Cool. Let's just go run that. I'll pick out one random directory and run it. So I have 6,000 of these, and unfortunately, this is going to take forever. It's going to take forever. At home in Texas, with a fast internet connection, it takes around 40 seconds. Here, far away from the data, on conference Wi-Fi, it's going to take longer than I care to wait. So we're just going to stop doing that. But I promise it takes a long time. And instead, we're going to ask for a bunch of machines. So I'm going to ask for 20 machines living in Virginia, close to where the data is. And this will be useful both because it will be local to the data. The data stored on S3 will get access to that same data. And it'll be useful because it'll have many machines. We can do this processing more quickly. So right now, I'm asking for a Dask cluster, and it's scraping my local environment, figuring out what version of Python I have, what version of pandas I have, et cetera. And it's now asking for a bunch of machines. This is all interactive stuff. I'm going to point out a bunch of these interactive pieces later in the talk. Right now, I'm just sort of going through, and you're going to see all of these things that are interactive and fun. If I was up here standing and waiting for this cluster to start up, I would feel very nervous because I wouldn't know what was happening. That would create stress. You would be nervous because you would be waiting. But right now, you're not nervous. You are hypnotized by a very simple progress bar up there, and you are happy. There's actually a lot of satisfaction from seeing little things move in your notebook. And we are really good at making little things move in your notebook. And that's actually really important. So I've got now 20 machines. I actually have them. I'm renting them from Amazon. They're downloading all the right packages. And I'll have them in about a minute. But again, I want to reemphasize, there's a psychological benefit to seeing a thing up here moving as we are waiting. And that psychological benefit is actually really, really important for sort of interactive data science workloads. This is using Rich, which is a lovely system to do interactive console-type visualizations. It's great. All my workers. Let's go and let's just map that function across all of those different directories. And so interaction number 2, I've got progress bars. This is now showing IPy widgets. And again, you can kind of feel the sort of the pleasantness of seeing that something's going to happen. Also looking at this is going to take a long time. So I'm actually going to ask for a bunch more clusters, bunch more workers. So I had 20 machines, let's get like 400 instead. Take about another minute. This will start going faster afterwards. And this progress bar is neat, but honestly, we can do better. So we're going to grab more. So I'm going to get more dashboard things. Let's see what we got here. Here we go. Yeah. So what's happening? In the top, if you've seen a Dask talk, I apologize. This is explained every single Dask talk. For those of you who are new, the top right plot here, every line corresponds to one core in my cluster. And we're seeing what that core is doing over time. Every little box is a Python function. So this little box, we were running the extract function that took 12 seconds. This computation is super simple. If we want a more complicated computation, there's lots of little flashy boxes up here. But we can just kind of see progress across our cluster. And it's satisfying to notice that things are moving along. Another progress bar over here. We're making some progress, but it's taking a while. Memory is low. Let's go and we care about, I guess, network here more. More network bound than anything else. So it's nice that I can kind of define my own workspace here and look at the things that are important to me. This workload is network bound. I'm looking at this and I'm seeing, I'm getting, peaking at around 250 megabytes per second. That's kind of what I expect coming off of Amazon S3. So I'm feeling comfortable. I'm using my resources well. And then hopefully, right about now, it looks like more workers are coming on. Remember, we started with 20 machines. Now we're getting up to 400. And so that top chart is just going up as more and more cores are being added. And our progress bar is, from way up here, is going to start moving more quickly. There we go. So we're going to wait here for another about minute as we're processing these 3 terabytes of PDFs stored in tar files. Let's just marvel at the fact that we're accessing very janky data in a very ugly way. But we are able to do this by renting several hundred machines and process this data relatively quickly in a couple minutes in a conference, and everything kind of works. And we feel good, right? These flashy lights are making us feel more comfortable. While we're waiting, ooh, look, one of our files had an error. We got a nice little signal, an error happened. That's actually okay. One of the directories was bad. We'll filter it out. We're almost done. After that happens, we're going to gather the little results. It's actually going to take a while. Usually this is fast, but again, across continents and conference Wi-Fi is going to be slow. I'm going to shift back to slides and come back in a second. Okay. So what did we see? We saw a lot of interactive elements, right? We saw Rich. As we were deploying our cluster, we got to see how that looked like, and that was fun. So IPy widgets, right? IPy widgets are fun. They're super accessible, very easy to use. We saw bokeh. So these charts are bokeh plots that were embedded inside of JupyterLab. JupyterLab allowed us to play with it. I'm actually going to go back very quickly to this. There's a JupyterLab extension for Dask, which allows us to connect to our cluster and have all of our different plots available. And that's really fun. There's like lots of plots I could show you. I didn't show you this one, but there's other little fun things we could play with. And what Jupyter gave us, what JupyterLab gave us, was a canvas to put all of those charts together. And so users, based on the workflow, can build a workstation that makes sense for them and helps to address a lot of the uncertainty that they feel from having their computation run remotely. And that's been very present. This is the most beloved feature of Dask. We interview a bunch of Dask users. We ask them what their favorite feature is, and about 80% of them say the dashboard, which for like a computational project is like a weird thing. I want them to say like how fast it is or how much it scales, but they just really like the dashboard. And having it in Jupyter is pleasant. So put that on a little bit more. This is mostly conference Wi-Fi's fault. It's just like bringing these little small results back from the cloud. Let's round a different example. So that's a very simple example of Dask. Let's play with a more complicated example. So if we make a NumPy array, right? We make a NumPy array, 100 by 100 array, and that would be just fine. If we wanted to make that, maybe a 100,000 by 1,000 by 1,000 array, that would be a bad idea. And so Dask gives us the ability to do more fun things. And then we can visualize what that array looks like. We can play with that, and we can look at x dot transpose and look at that. And we want to do mean across an axis. What do I want to do here? Equals 0, I guess. No, it's not the right one. It's cool because I'm trying to get this square. That's not the right one either. That's what I wanted. Right. So I can kind of play around with looking at these large computations, and I get to see what's happening, and that's very fun. Let's go and connect up to a local machine. We'll just start running this computation. Hopefully this works. And so again, we get to kind of see what's happening. This is running just on my laptop, not in a big cloud cluster. But again, it's a satisfying thing to experience parallel computation. So that's JupyterLab and interactivity with Dask. Is my data still not here? Okay. So real-time diagnostics are great. Dask has these. Jupyter allows us to incorporate those inside of it, and that's very pleasant. The system we use to do that incorporation, we've actually made more general. Companies like NVIDIA have taken that. They do that for GPUs now. You can do that if you've got your own systems. It's fun to have kind of bokeh plots in Jupyter. What we found is, trying to think. I had this whole thing about historical diagnostics. I think I'm going to skip that for now in the interest of time and move on to a different topic. Yeah, moving on. Okay, so again, talk number 1, interactivity and diagnostics. Computing sucks. Interactivity makes it not suck. Topic number 2, cloud notebooks with Dask. Totally different topic. If before we were talking about JupyterLab things, we're talking more about JupyterHub things. Many people like using Dask to access cloud data. Many people like doing that from Jupyter notebooks in the cloud and creating large-scale interactive experiences. I see people in the audience who try to do that as well. It's a fun thing to do. It's also very hard. But in general, like JupyterHub and Dask, you would think to put them both on Kubernetes, everything works out lovely. We've done this a lot. A lot of the Dask developers work on these sorts of things very frequently. A good example is the Pangeo project. People are familiar with Pangeo. Can you wave your arms wildly if you're familiar with Pangeo? Yeah, Pangeans, happy friendly Pangeans. Pangeo is great. Pangeo is a combination of JupyterHub and Dask, or other things, running often on the cloud, sometimes on HPC. And the user experience was such. You would log onto a website, You would authenticate with something like GitHub or Globus or some other thing in your organization. You would then get a Jupyter notebook. Inside that Jupyter notebook, you would ask for a Dask cluster, and you would then use that to process lots of data. You would then do science. Right? These are all images that were made from various distributed Dask things running on Jupyter hubs in the cloud. It was fun. We actually did a lot of really good work. It was also a pain in the butt. It was a pain in the butt because different users wanted different things. It was very, very hard to construct a Jupyter system, a Jupyter hub system that could serve many different kinds of users at once. Adding Dask into the mix made it very challenging. In particular, things were just a little bit too rigid. So let's look at some examples of things that people wanted that were really hard to support. And if you're like an IT person, maybe these sound familiar to you. We had to match software environments. Someone would pip install scikit-learn on their notebook and be confused why they didn't get scikit-learn also on their Dask cluster. People would have development scripts that they were running on and were confused why those weren't remotely available. People wanted to access data. They had installed their AWS permissions on their notebook, but for some reason couldn't access data remotely. They sometimes left clusters on for long periods of time. That was very expensive. We were giving them big guns to play with, and they were playing with them, and they were misusing them sometimes. They also often wanted lots of different requests. Hey, I've got a collaborator who has data in Europe, or has data in the States, or who has data in South Africa. I want to use SSDs for this workflow. Can I have access to GPUs, please? There's lots of different requests that they had that were very hard to support. And we found that we had to support many different groups, all with these different constraints. And that was a challenge. And so there are many products that do this now. I'll give you a list later. There's 2i2c, excellent group. There's Nabari coming out of QuantSight. Domino Data Labs has a Dask Jupyter thing. Google Dataproc has a Dask Jupyter thing. This is like a common thing that exists. I'm actually somewhat pessimistic about this model. So I've shifted my direction a little bit. I want to tell you a little bit about that direction. So let's go and back to my notebook. When I ran this example, I was not running this from a cloud notebook, but I was able to access data on the cloud. I actually ran this example from my notebook. This is on this laptop. I'm driving my Dask cluster from my laptop. And we've started playing with the thing. So I'm actually supposed to say, this is like the for-profit version part of the talk. I'll very briefly pitch a product. I'll get back to open source in a second. We kind of gave up on trying to match a Jupyter environment or a cloud environment to a Dask cluster. Instead, we do everything very dynamically. So I'll give an example. Let's ask for 20 workers. And let's try running that in, what's the EU? Is it EU Central 1? Is that what's local here, I think? Sorry? I couldn't hear you, but I'll just, okay. I'm gonna see if this works, we'll find out. Let's try ARM. Let's try ARM chips, because they're pretty cool these days. And let's look for maybe like 16 CPUs each. And also, let's actually, while I'm playing around, let's go into Dask. And let's just go 1,000 lines down. Let's put a print statement in here. All right, so I'm modifying Dask. And let's install that into my environment. Cool. Hopefully that worked. Let's make a cluster. Oh no, module not found, import coiled. Well, this is confusing. Oh, that's strange. Nope, that's confusing. Let's go over to tutorial. Great. Okay, so I am now dynamically trying to mimic this laptop. Instead of in configuration ahead of time, I'm doing everything dynamically. So I am capturing the local packages on this laptop. If I have a development version of something installed, I'm wrapping up a wheel and shipping that out to the cluster. I am asking for those machines on the fly. There's no Kubernetes cluster I've set up because I don't have a Kubernetes cluster sitting in EU Central 1. I am grabbing my AWS permissions on this laptop, so I have an AWS config file, and I'm using STS, Secure Token Service, to generate secure tokens I can ship off to that cluster. I am on the fly creating a cluster, a Dask cluster, that I can run from anywhere that I can run Python. And that allows me to scale out a data science workflow from anywhere, from a JupyterHub deployment, from my laptop, from GitHub Actions, from 2i2c, from Anaconda notebooks, from any place. And we found that this approach is a little bit magical, but also very effective. We're able to match and scale out any existing Jupyter deployment without having to do a lot of sort of predefined configuration. We found there was a lot of pain in configuring things to work well. We've just kind of given up on configuration, and we're doing everything dynamically on the fly. And that's been very effective. So this is like our approach that we do now, or at least that people around me do. And it's been fun. It's definitely the best experience we've had. So let's go back to slides. Actually, I'll do a little bit more. Let's see. What's also nice, so we had issues with people who, again, had clusters running all the time, or didn't know why things were slow, or were broken in some way. And we can go and look at all those clusters. Right? So let's go. I think if we go out to the booth right now, let's go. So this is the internal Dask engineering team at our company. So I work for Coiled, by the way, called a for-profit company based around Dask. And I can see that I am running 2 clusters. This is my big archive thing. Let's actually shut down that cluster. That's kind of expensive. There's a cluster I'm starting right now. There's a bunch of other things my colleagues have worked on in the past. I'm actually looking here. My colleague Miles was playing around. Looks like he had an error. Let's go see and look what Miles was doing and where he got that exception. Right, so, he's got mismatched version types found. Let's go find that code. Right, okay, here we go. Right, and so I can go and I can play with and I can experiment with and I can investigate what people using Dask are failing with and how to help them. And I can get some signals about, hey, this workload is network bound. You might want to try ARM chips. This workload is hitting disk, but you don't have a local disk around. You might want to shift that around. There's actually a lot of interesting interplay we're seeing in the sort of choices between your Python code and observability metrics and your sort of cloud infrastructure. It's like interesting optimization to be made in that space, and we're kind of excited about that. For example, we've just been playing with ARM recently. We got that very smooth in the last few days. We're seeing like a 30 to 40%, 20 to 40% cost improvement just by like adding an ARM equals true flag. Like Intel should be concerned. You should all switch to ARM. It's pretty easy now. Anyway, those are some things. I apologize for like the slight for-profit demo. Again, there are other excellent solutions that do this kind of thing. They all integrate Jupyter and Dask together. Again, that's not the approach that I'm recommending at this point. I think it's nice to be sort of dynamic. But there's other really good solutions out there. I like Nabari. Nabari is like the full open source one. It's fun. You can just, it's like all GitOps and Kubernetes. And that's it. Thanks for your time. To summarize, distributed computing sucks. Interactivity is really helpful. And coupling, I think, is hard and to be avoided. And so I'm recommending that Jupyter folks start to decouple from Dask when they can. So that's it. Thanks.
Any questions?
Hi. My question is about Conda packages. When you have a local Conda package and you're NARM Apple like yours, and you want to compute on an Intel machine on AWS, how does it handle if the Conda package can be compiled in both architectures? I think it works. But if it's something that is very local, how does it handle?
Yeah, so let's give a couple examples for that. So let's say that I'm using Windows and I'm using NumPy, and NumPy depends on MKL, which is common in Windows. But on Linux, I don't have MKL, I have OpenPlus. Yeah, So if you're transferring a specification of Conda packages between architectures, you're kind of depending on Conda Forge or Conda to have mostly equivalent packages. So we find what matches, we remove what doesn't, and then we ask the Conda solver to fill in the gaps. So this is the not the easy version, but this is the simple case. You might also have something that's very custom to your own environment. Maybe you have some hard-coded C++ code that you've compiled to just that architecture. Yeah, we can't ship that over. What we find more often, though, is that that kind of code is often already encoded in a Docker image, or it's encoded in an apt file, or it's encoded somewhere else. The challenge that we find with users is mostly in sort of Python code that shifts more rapidly. They're less frequently updating their deep core C++ libraries as they are pandas, for example. Does that answer your question?
Kind of, but if in your example you use the MKL, and if you want to compute this on a norm machine, how do you recompute everything, recompile?
Yeah, so we don't try to move MKL. You're probably running a Python function. You're running numpy dot or something. And we ship numpy dot over to the other machine, and then the other machine calls numpy dot. It has a different set of packages. And
in fact, the closest library that can match.
Yes.
Okay.
And so there's some fuzzing that has to be done, which almost all the time is perfectly fine.
Okay, thanks.
Yeah. If you're interested in more of this, if you go to blog.coil.io, there's lots of interesting blogs on packaging. How do we do this so quickly? Python packaging is crazy. Trying to make this work across every way someone can install a package is crazy. There's some very interesting engineering that happened behind this. If you're interested, there's a lot of information you can play with or go and learn about.
Any other questions? In this case, I have one question. So when you have a Dask cluster that you start a number of machines, do you have any tips on avoiding forgetting about shutting it down eventually at the end?
Yeah, so that's a common issue. If you use coiled, we'll shut it down by default after 20 minutes of inactivity. That's configurable. There is, I think in Dask, there's the death timeout keyword. Well, apparently it does nothing. Yeah, so there are ways to do this in Dask. In Dask, as with many projects, there are always ways to do the thing that you want. Sometimes the challenge is configuring it robustly and configuring it well. And that's where I think some of these platforms that run Dask for you, like Coiled, but also some of these other platforms, can save a lot of headache. We manage millions of Dask clusters these days that are run all the time. And many of them are ours, and we care a lot about those costs. And we've done everything that we can to reduce those costs. Idle shutdown is one of the very first things that we do.
OK, thank you.
If you all want to learn more, there's a booth. Come on by. We've got fun shirts. We've got stickers. We've got people who know about Dask and pandas and things. So thank you all for your time.